In the name of Allah, the most gracious, the most merciful. O Lord, expand my chest for me, ease my task for me, and untie the knot from my tongue so that they may understand my speech. In the 5th episode, we discussed how we tackled most of the practical problems or challenges we faced with the differential release, and we got to know the concept of bias current in detail. In this episode, we will explain the operating characteristic and the settings of the 7UT release, which is one of Siemens' devices. So stay with us. The rise of a nation. The differential protection graph shows operating. This graph shows the relationship between operating and restrained current. The characteristic can be shown in 2 or 3 zones. Zone A is a straight line from I differential 0 to the start of Zone B. Here, the relay trips if the differential current exceeds I beta. Zone B has a slope K1 starting at Zone A's end and ending at Zone C's start. The relay trips if the differential current exceeds the slope times the restrained current. Zone C has a slope K2 starting at Zone B's end and continuing. Zone A, red, from I differential 0 to Zone B. Relay trips if current exceeds I beta. Zone B, yellow, slope K1, from Zone A's end to Zone C's start. Relay trips if current exceeds slope times restrained current. Zone C, blue, slope K2, from Zone B's end. Relay trips if current exceeds K2 times restrained current minus note, derived from line equations. With settings like note, T1, K2, and IB, I can draw these characteristics. This area starts at end of Zone A and ends at beginning of Zone C. Relay trips if differential current slope times restrained current. Zone C, third area, has slope K2. It starts at end of Zone B and continues. Relay trips if differential current K2 times restrained current, note, derived from line equations. If settings, note, T1, K2, IB, known, I can draw operating characteristics and find value for relay trip. Test by selecting curve points to simulate relay trips. The relay should send a disconnect signal through this region. If the differential current value exceeds the value of K2 multiplied by I restrain minus I restrain note. This equation can be easily derived from the straight line equations. If the settings parameters, which are I restrain note, T1, K2, and IB, are known in advance to me, then I can draw these operating characteristics very easily. Know the value to trip the relay. We test points on each curve, placing some above to trip the relay, and others below for stability. This ensures correct relay operation. To learn these equations, stay tuned for the example. Example: draw Siemens details, write equations, explain Diggs-Ivor details. First, consult the relay manual, extract Siemens details, and present them. We place points below the curve to simulate external fault conditions, ensuring the relay remains stable without issuing a trip signal. To learn how to derive these equations and their applications, stay tuned for the example. Draw Siemens specific details, write related equations, and explain insights from the Diggs-Ivor program. Start by consulting the relay manual for Siemens details. Setting 1251 equals 0.2I over in, a percentage, as for setting 12126A. Draw the details specific to Siemens, then write the equations related to them and explain the details extracted from the Diggs-Ivor program. The first step in the drawing is to go to the manual for this relay and extract the specific details from Siemens and present them in the following format. Each setting has a specific number. The I differential inside is 1221, equating to 0.2I over in, a percentage. Setting 12W6A is 1221, equating to 2I over in, also a percentage. Settings 12W6A and 1.2.3.6A allow time delay in special cases. Usually, the differential is instantaneous with 0 time. 1.2.3.6A are options. In case although, time delay is added to differential protection in some special cases, but usually the differential is instantaneous and its time is 0. Now we want to determine the number of lines in this characteristic. Then we find the equation of the straight line for each line and find the intersection points between each pair of lines. We need to redraw the trip characteristic, placing each value according to its setting. We will review to find the equation of the straight line and apply it to the characteristic. If we assume a line between 2 points, x1y1 and x2y2, what is the equation of the straight line? First, find the slope, y2, y1 over x2, x1. The equation of the straight line f is So, if we assume that we have a line between 2 points, the first point x1, y1, and the second point x2, y2, what is the equation of the straight line for it? First, we find the slope, which equals y2, y1 over x2, x1. Therefore, the equation of the straight line f of x, let's cut x1. Hence, equation of the straight line f of x, y2 equals slope times x2 minus x1 plus y1. y1 was minus y1. Move to other side, now plus y1. Consider a numerical example. Between points x1 nor 2, y1 nor 4, and x2 var 3, y2 var 6. Calculate slope y2 y1 over x2 x1 var 6 to 4 over 3 to 2 r2. And it equals 6 minus 4 over 3 minus 2, which equals 2. So f of x equals y2, which equals the slope. This is the equation of the straight line. The slope multiplied by x2 minus x1 plus y1. Now we substitute the value of the slope. Therefore, f of x equals y2, which equals 2, the value of the slope, times x2 minus x1. Here, x1 equals 2 plus y1, where y1 equals 4. Thus, the equation equals 202, 2 plus 4. Substitute 2 inside, it becomes 202, 4 plus 4, 202, 4 plus 4. Open the parenthesis, 4 cancels plus 4, fx, over y2, 202. Simplify, fx over y or 2x. If x of 3, y or 6. If x of 2, y of 4. From the line equation, fx over y2 or slope, x2, x1, plus y1. If x1 is 0 and y1 is 0, y of slope, x, passing through the origin. X over 3 gives y over 6. X n over 2 gives y over 4 using the equation. From fx over y2 over slope, x2, x1 plus y1. 4 cases, x1 over 0, y1 over 0, so y over slope. X through origin, x1 over 2.5, y1 over 0, so y over slope. X 2.5 through positive x-axis. If x1 are 0 and y1 are 0, the line equation is y iron slope times x, and the straight line passes through the origin. If x1 are 2.5 and y1 are 0, the line equation is from y iron slope times x 2.5. And the line passes through this point on the positive x-axis. If x1 are 0 and y1 are 7, the line equation is y at slope times x plus 7. The line passes through a point on the y-axis here. The line equation is from y-axis slope x, 2.5, and the line passes through this point on the positive x-axis. If the value of x1 is exactly 0 and the value of y1 is precisely 7 or alternatively 7, then according to the light equation, the value of y will be equal to the slope multiplied by the value of x plus 7. Consequently, the straight line will intersect at a specific point on the y-axis, which is this particular point. If the value of x1 is specifically equal to 2 and the value of y1 is precisely equal to 3, then the line equation y is exactly equal to slope x2 and all of them plus 3, and a straight line will pass like this. If the straight line is constant, meaning that the value of y does not change with the change in x, in this particular scenario. So the slope will equal 0, and thus the equation of the straight line will be y2 equals y1. What is the equation of the straight line for the constant line between the 2 points x1 equals 2, y1 equals 3, and the second point x2 equals 5, y2 equals 3? Notice that y1 equals y2. Point 53 shows a constant line, slope 0, y3. Find differential protection line equations. X is I bias, y is I by function. In this case, we say that the line is constant and that the slope equals 0, so the equation will be y equals 3. Now we want to apply the same method as before to find the equations of the straight line for the characteristics of differential protection, knowing that the x-axis is I bias or I restrain and the y-axis is I by function or I operating, or I bias or I restrain and I-axis is I branchial or I operation. Let's start with the first line, representing a constant where the value remains unchanged, equaling y. The second line's extension passes through 0, meaning y equals slope times x, or I differential equals slope 1 times I bias. Note that the line segment's extension doesn't consider the curve. The third line doesn't pass through the origin, but another x-axis point called the setting at base point 2. Here, the line equation is y equals slope times x minus its x-axis intersection. Line at 0, y as slope, x I diff as slope, I bias. Line extension ignores curve. Third line crosses base point 2 on x-axis, not origin. Equation, y as slope, x base point 2, 2.5. Line 3, I diff as 0.5, I base 2.5. Fourth line, constant like first. Line 4, I diff as 7.5. As for the third line, we will notice that it does not pass through the origin point, which is 0, but rather passes through another point on the x-axis, referred to as the setting at base point 2. When the straight line passes through a point on the x-axis, the equation of the straight line will be y equals slope times x minus its intersection point on the x-axis. And this tells us that it is base point 2, which equals 2.5. Therefore, the equation for the third line, line 3, is I differential equals half, which is the slope times I base minus the base point 2, which equals 2.5. As for the fourth line, it is a constant line, and its concept is exactly the same as that of the first line. Thus, the equation for the fourth line, line 4, will be I differential equals 7.5. Also, friends, if they ask for 7.5, the 7.5 we took from the setting where the I differential is greater than or equal to 7.5 according to the setting and the high setting for the I differential. So, we have 4 straight lines, and each straight line has its own specific equation. Therefore, we have 4 equations, 2 of which have a differential current that does not depend on changes in the I bias current, which are the equations for the first and fourth straight lines. This is because it does not contain a slope and represents constant differences. On the other hand, the equations for the second and third lines contain slopes, each with its own specific slope. Therefore, the value of the differential current depends on the change in the I restraint current or I bias current. In summary, the 4 equations are as follows. Line 1, I differential equals 0.2. So, I want to be part of France. I diff out of 0.25, I bias, I diff out of 0.5, I bias 2.5, I diff out of 7.5. Any differential will be 0.5 and the balance will be 4. Any differential will be 0.5 and any differential will be 0.5. Inspiring. Now if I tell you that the value equals 1, what is the value needed to send to which of the 4 equations should I use? First, we substitute the value in each equation. Now indeed, the first equation doesn't have it to substitute, so the value in the first equation remains as it is, which is substitute the E base value, and if not equal to 1 in the second equation, differential current is 0.25. Substitute the E base in the third equation, differential is 0.75. Substituting I bias in the fourth equation shows it doesn't depend on I bias, so I bias is 0.5. Thus, I can't decide on the right equation without knowing each equation's limits. Use the first equation if I bias is in the red zone. Use the second equation if I bias is in the yellow zone. Use the third equation if I bias is in the blue zone. Use the fourth equation if I bias exceeds the blue zone. Thus, don't substitute I bias incorrectly. Know the start and end limits of I bias in each area independently to find these limits. The second equation should be used if the E base value is within the yellow zone. Third equation should be used if the E base value is within the blue zone, and the fourth equation should be used if the E base value exceeds the blue zone. Therefore, it is not permissible to substitute the I bias value in a place other than its correct equation. Accordingly, the beginning and end limits of the I bias value in each region must be known independently. To find these limits, if 2 straight lines intersect in the Cartesian plane, they meet at a common point. For 2 intersecting lines, the first line's equation is y1, warm 0.6x, 2, and the second line's equation is y2, warm 0.2x plus 1. They intersect where y1 equals y2, which occurs at x of 0.5. Substituting x of 0.5 into either equation gives the same result, confirming the intersection point. Thus, y1 equals y2 and equals 2.5. Applying this concept helps find the boundary value for each characteristic to determine the appropriate equation for the required value, to find the intersection point A. The first equation equals the second when x is 0.5. Substitute x as sought 0.5 into either equation to find y1 as y2 at 2.5. Apply this method to find boundary values for the current characteristic and the appropriate equation. To find intersection point A, set the first line's equation equal to the second's. For point B, equate the second and third lines. For point C, equate the third and fourth lines. Thus, for point A, equate the first and second lines, then find I. Present I in either equation. 0.2, 0.25 I, so I, 0.2, 0.25, 0.8. Between the first and second lines, we equate the equation of the first line with the equation of the second line. To find the intersection station B between the second and third lines, we equate the equation of the second line with the equation of the third line. To find the intersection station C between the third and fourth lines, we equate the equation of the third line. To find the intersection point A, we set the equation of the first line equal to the equation of the second line, and then we find the value of I. This value we found for I can be presented in either of the two equations, the equation of the first line or the equation of the second line. Therefore, 0.2 equals 0.25I, which means that I equals 0.2 divided by 0.25, which equals 0.8. Substitute 0.8. I differential 0.2. A is R on x-axis, I on y-axis. When we substitute 0.8 into either of the previous equations, the value of the I differential will be 0.2. Therefore, the value of A, or point A, is R, which is on the x-axis, and I differential is on the y-axis. X and the differential of the y-axis. To find point B, equate the second and third lines to get I bias as 5. Substitute to find I differential as 1.25. For point C, equate the third and fourth lines to get I bias as 17.5. and I differential as 7.5. Then we take this 5 and substitute it into either of the two equations, the equation of the second line or the equation of the third line, to find the value of I differential. Therefore, the value of B, or intersection point B, will be I bias equal to 5 and I differential equal to 1.25. As for intersection point C, we do the same thing by setting the equation of the third line equal to the equation of the fourth line to find the value of I bias, which will be 17.5. We substitute this value into either of the two equations because it's a common point to find the value of I differential at point C. Therefore, the value of I differential at point C will be 7.5, making the value at point C 17.5 for I bias and 7.5 for I differential. 5x and 7.5, like any bifrankial. What does it mean when I tell you that there is a point at equality? This means that the value equals and the value equals, and these values can either be in amperes or in percentage. These numbers mean that if the value of IBS equals 5, then the value of the differential current must exceed 1.25 in order to send a trip signal to the circuit breaker. Now we can say that the equation of the first line can only be applied if the IBS domain is within a specific range between 0 and 0.8. In a specific area between the value of the differential will remain constant at 0.2 throughout this period, as shown in this table. However, the differential relay will not issue any trip signal unless measured value of the differential current exceeds 0.2. As for the equation of the second line, it can only be applied if the RBOS domain is within a specific range between 0.8 and 0.5. The value of the differential current will remain within a variable range between 0.2 and 1.25, where 0.2 is the result of substituting 0.8 into the equation, and 1.25 is the result of substituting 5 amperes as I Boas into the second line's equation. However, the differential relay will not issue any trip signal unless the measured value of the differential current exceeds 0.2 if the value of I Boas is 0.8. If the value of IBS changes and becomes 5, for example, then the differential delay will not start the trip signal unless the value of the differential current exceeds 1.25. Similarly, the equation of the third line can only be applied if the IBS domain is within a specific range between 5 and 17.5, in a specific range between 5 and the value of the differential current will remain in a variable range between 1.25 and 0.5, where 1.25 is the result of substituting the 5 in the third line equation, and 0.5 is the result of substituting the 17.5 in the third line equation. As for the equation of the fourth line, it can only be applied if it is in a range greater than or equal to 17.5. The value in this area will remain constant at 7.5 throughout this period, as shown in this table. We can summarize all four equations as shown in this table and then represent them as in the following figure. Now, let's return to the previous question again. If the value of I bias equals 1, what is the necessary differential current to send a tripping signal to the circuit breaker? Which equation should I use? I can tell you that it should be substituted into the equation of the second line only. This is because the I bias range is between 0.8 and 5. Therefore, when substituting the value of I bias equal to 1 into the second line's equation, the value of the I differential current will equal 0.25. This means that if the value of I bias is 1, the relay will not issue a trip signal to the circuit breaker unless the value of the differential current exceeds 0.25. The value is 0.25. And now I can easily place the point 1.25 on the differential curve. Easily. Explain the S-curve of Siemens UT relays. 3 steps: determining line numbers, finding each line's equation, and identifying intersections. These steps apply to various differential relays. The green area in the trip characteristic, Waliha, will be explained after the break. Modern relays detect city saturation, causing differential current and a maloperation, a false trip. We apply the same steps to most differential relays from different manufacturers, though the curve shape varies and involves minor calculations. The green area in the trip characteristic is Waliha, specific to this relay type, explained after the break. Modern relays detect city saturation at external fault boundaries with high currents, generating differential current, leading to maloperation or false trips. This happens when the relay doesn't operate on intended faults. If the differential current I differential compared to I restrain causes I restrain to be high, the point moves from A to B, and then the differential current increases, with a slight decrease in restrained current, leading to the tripping area. Modern relays detect city saturation, causing differential current and a maloperation or false trip. If I differential compared to I restrain is high, the point shifts from A to B and the differential current increases. This increase, with a slight decrease in restrained current, moves the point into the tripping area at C, indicating CT saturation. The add-on stabilization function blocks differential protection during the first quarter cycle of the fault, requiring I restrain to exceed 4, and remains active for 15 cycles, with one cycle equaling 20 milliseconds at 50 Hz. The relay works so that if the dynamic behavior of point-A differential makes I restrain high, increasing differential current. Add-on stabilization blocks protection. I restrain must exceed 4, block active for 15 cycles, each 20 minutes at 50 Hz, 16.67 minutes at 60 Hz. Operation point must enter pink area for stabilization. At point C, the CT has entered the saturation phase. Thus, add-on stabilization blocks the differential protection in the first quarter cycle of the fault. I restrain must exceed 4 as shown and remains active for 15 cycles, each 20 minutes. 50 Hz or 16.67 minutes at 60 Hz. It's crucial the operation point enters the pink area for add-on stabilization to act and block differentially. And one cycle equals 16.67 milliseconds if the network frequency is 60 Hz. We want to emphasize a very important point that the operation point must enter the pink area for the add-on stabilization to interact and perform the differential block. Add-on stabilization blocks. If the point enters the white blocking area without first entering the pink area, then moves into the tripping area, the differential will issue a trip decision. An engineer might ask, what if an external fault causes a CT to saturate, triggering add-on stabilization and block differential protection, while an internal fault occurs? If the relay detects the operation point moving towards the fault characteristic for at least one cycle, it will cancel the blocking, even if the add-on stabilization time hasn't expired. Regarding harmful harmonic constraints, if a CT saturates and add-on stabilization activates block differential protection during an internal fault, the relay will cancel the blocking if it senses the operation point moving towards the fault characteristic for at least one cycle. In this case, As soon as the relay senses that the operation point starts to move steadily towards the fault characteristic for a duration of no less than 1 cycle, it will automatically decide to cancel this blocking, even if the time for the add-on stabilization set in the settings has not yet expired. As for the harmful harmonic constraints in the settings, in this image, as for the appearance in this picture, as we mentioned before, when transformers are activated, there will be a high current draw, which can reach several times the normal current. When analyzing these currents, it was found that they contain a high percentage of second harmonic current compared to the actual fault current. It was possible to distinguish between currents and implement a differential block if the second harmonic current exceeded 15% of the fundamental current. For example, if the fundamental current is 1 ampere, the second harmonic must exceed 0.15 amperes to trigger the block. Similarly, for a 2 ampere fundamental current, the second harmonic must be 0.3 amperes. Overexcitation in transformers due to frequency changes can increase differential current, leading to block activation, so that the relay in France issues the block. If the fundamental current is 2 amperes, the second harmonic must be 15% of this. Overexcitation in transformers increases differential current with odd harmonics. The third or fifth harmonics help detect this. The third harmonic circulates within the delta connection. The fifth harmonic is preferred. If the fundamental is 1 ampere at 50 Hz, it must exceed 0.25 amperes at 250 Hz. For the second harmonic, it's 100 Hz. Odd harmonics detect phenomena. The third harmonic current stays within the delta connection in transformers, not used for overexcitation detection. If the fundamental current is 1 ampere at 50 Hz and the fifth harmonic setting is 25%, it must exceed 0.25 amperes at 250 Hz for the relay to block differentials. If the fifth harmonic is set at 25% of the fundamental, the current must exceed 0.25 amperes at 250 Hz. For the second harmonic, it's 100 Hz. The fifth harmonic requires exceeding 0.25 amperes at 250 Hz for a differential block. If the fundamental is 2 amperes at 50 Hz, fifth harmonic must exceed 0.5 amperes at 250 Hz for the block. Harmonic restraint operates independently per phase, so an increase in one phase's harmonic current causes a block only on that phase. A harmonic restraint on the red phase triggers a block there, while yellow and blue remain stable. A fault on yellow or blue triggers a trip on those phases. The relay's cross-block function allows reflecting a block from one phase to others. The percentage of the fifth harmonic current must exceed 25% of 2 amperes, which means it should be 0.5 at a frequency of 250 Hz for the relay to issue. A differential block. Since the harmonic restraint operates independently for each phase, an increase in the harmonic current on one phase without affecting the others will create a differential block on that specific phase only. If a harmonic restraint occurs on the red phase, it triggers a differential block only on that phase, while yellow and blue phases remain stable. A fault or differential current on yellow or blue phases causes a trip on those phases. The relay's cross-block function allows a block on one phase to reflect onto others without a differential block. If the second or third harmonic current increases on the red phase and cross-block is active, the differential block extends to yellow and blue phases, blocking all phases. Cross-block activation spreads red phase harmonic current block to all phases. Without it, cross-block activation moves the red phase block to yellow and blue, blocking all. If inactive, it stays on red. It's usually active. If the cross-block is not activated, the block on red phase stays there. Moving to blue phase, the cross-block is usually activated and can be time-limited as shown. To increase tripping characteristic during startup, activate it to raise curve or reduce sensitivity. This suits motor startup, allowing inrush current to pass, ensuring safety against false relay operation. Restrained current must exceed normal current. If near zero, it indicates this is suitable at the moment of starting the motors to allow the inrush current or starting current to pass at the moment of startup. This provides additional safety against any expected false operation of the relay in normal operating conditions. The value of the restraining current should be greater than the normal current. But if the value of the restraining current approaches zero, this indicates that, and the beginning of its value increased significantly over time. On one of the phases, and with a value less than 12.51, the current increase feature will be activated. The factor in 1252 increases it. With increased current or voltage, curves shift proportionally. After time in 12.53, curves return to original state. The current graph is as follows. The curves shift proportionally, and they definitely won't stay at that moment forever. After a certain time indicated in 1253, the curves will return to their original state. Especially the graph of the current is as follows. It shows current sensitivity, considering fixed current errors, relative current errors from conversion, voltage, current. This area considers current errors from voltage regulator changes. This ensures current stability. Regarding current errors, this area considers voltage regulator changes. It ensures current stability at high currents, ensuring operation at that moment. This area also considers current errors from voltage regulator changes. This ensures stability and operation at any moment, regardless of current increase, especially at high currents, which may lead to one of the cities entering a phase. This ensures that we can operate at that moment. Regardless of the high value of the L, or even the occurrence of any previous reason or otherwise, this L, it will be activated during. With this amount, we will conclude today's lecture. Join us in the next episode, where we will explain the current and the related topics. Glory be to you, O Allah, and praise be to you. We bear witness that there is no deity but you. We seek your forgiveness and turn to you in repentance. We'll meet you in good.